Implementation of Relativity Space's Terran rocket by Q4 2025, a comprehensive overview. Introduction. Relativity Space, an innovative aerospace manufacturer, is set to transform the landscape of space launches with its ambitious project, the Terran rocket. Targeted for implementation by the fourth quarter of 2025, this project has secured a substantial funding allocation of $750 million, primarily earmarked for leveraging advanced 3D printing techniques. This report provides a detailed overview of the implementation process, structured into 4 key development phases, each critical to the successful launch of the Terran. Funding and technological innovations. The $750 million funding commitment is a significant boost for Relativity Space, allowing the company to advance its proprietary 3D printing technology, which is central to the rocket's design and manufacturing process. This approach is expected to reduce material waste and production time compared to traditional manufacturing methods, making the Terran not only cost-effective but also highly adaptable to various payload requirements. Key development phases. The development of the Terran rocket is broken down into 4 critical phases. 1. Phase 1, Design and Engineering, Q1 2022, Q2 2023. This initial phase focuses on the engineering design of the Terran rocket. Relativity Space's proprietary 3D printing technology will be utilized to design components that require less material and time to produce. The engineering team is working to ensure that the rocket is both reusable and capable of accommodating a variety of payloads. The emphasis during this phase is on achieving a design that maximizes efficiency and adaptability. 2. Phase 2, Prototyping and Testing, Q3 2023, Q1 2024. Following the design phase, Relativity Space will move into prototyping, where initial models of the Terran will be constructed. This phase will include rigorous testing of the rocket system's materials and performance under conditions that simulate actual launch environments. The goal is to identify any potential issues early in the development process, allowing for adjustments before full-scale production begins. 3. Phase 3, Production and Integration, Q2 2024, Q4 2025. After validating the prototypes, Relativity Space will commence full-scale production of the Terran rocket. This phase will involve the integration of various components into the final rocket structure. The company's advanced 3D printing capabilities will be crucial during production, enabling faster turnaround times and reduced costs. This streamlined production process is expected to enhance the overall efficiency and reliability of the rocket. 4. Phase 4, Launch Preparations, Q4 2025. The final phase focuses on preparations for the inaugural launch of the Terran rocket. Activities during this phase will include final inspections, integration with ground support systems, and obtaining necessary regulatory approvals. By the end of 2025, Relativity Space anticipates conducting the rocket's first flight, marking a significant milestone in its efforts to establish a robust launch service for both commercial and government payloads. Common themes and differentiation. The implementation of the Terran rocket has been consistently reported across various sources, highlighting several key points. Innovative 3D printing technology. The use of advanced 3D printing techniques is central to the rocket's development, allowing for rapid production and design flexibility. Structured development timeline. The 4-phase approach provides a clear framework for the project, ensuring a systematic progression from design through to launch. Target launch date. All sources emphasize the Q4 2025 target for the rocket's inaugural flight, underpinning the urgency and significance of the project. However, there are variations in the sources regarding the specific technologies employed in the 3D printing process and the financial implications of the project. Some sources focus more on the technical challenges and innovations, while others delve into the broader financial landscape affecting the aerospace industry. Timeline of events. To summarize the progression of the Terran rocket's development, the following timeline outlines the key milestones. Q1 2022, commencement of the design and engineering phase. Q3 2023, transition to prototyping and testing phase. Q2 2024, start of production and integration phase. Q4 2025, target for the inaugural launch of the Terran rocket. Conclusion. The Terran rocket represents a significant leap forward in aerospace technology driven by innovative 3D printing techniques and a structured development process. With its projected launch by late 2025, Relativity Space is not only positioning itself as a key player in the commercial space launch market but is also paving the way for future advancements in rocketry and space exploration. The successful implementation of this project could redefine launch capabilities and contribute to the growing demand for reliable and efficient access to space. The implementation of Relativity Space's Terran rocket by Q4 2025 represents a significant shift in the aerospace industry, particularly through its reliance on advanced 3D printing technologies. Here are key counterintuitive insights from the detailed development plan of the Terran 1. 3D printing versus traditional manufacturing. While traditional aerospace manufacturing has emphasized precision and robustness, the heavy reliance on 3D printing in the Terran's development suggests a pivot towards a more flexible and iterative manufacturing process. This could lead to faster production times and lower costs, which run counter to the long-standing belief that aerospace components require extensive machining and complex assembly processes. 2. Funding allocation. The $750 million funding primarily earmarked for 3D printing techniques may seem disproportionate compared to traditional aerospace budgets, which often allocate vast amounts for R&D on materials and propulsion systems. This allocation indicates a belief in the transformative power of additive manufacturing to reshape the rocket development landscape, suggesting that innovation in manufacturing could be just as crucial as advancements in propulsion or aerodynamics. 3. Phase development approach. The structured four-phase approach might appear overly cautious in a rapidly evolving market where time to market is critical. However, this methodical process allows for thorough testing and validation of each component before moving to the next phase, which can ultimately lead to a more reliable and effective launch vehicle. Contradicting the notion that speed is always paramount in aerospace. For reusable launch systems, the design of the Terran emphasizes reusability, which is often perceived as a trend limited to well-established players like SpaceX. Relativity's commitment to a reusable rocket supported by 3D printing challenges the narrative that reusability is only achievable through extensive funding and existing infrastructure. It suggests that new entrants can innovate and compete on sustainability without the extensive historical baggage of traditional aerospace companies. 5. Integration of various payloads. The Terran's adaptability to various payload requirements challenges the common view that rockets must be highly specialized for specific missions. This adaptability could redefine market expectations, allowing for a broader range of missions without the need for entirely different rocket designs, which traditionally consume more resources and time. 6. Testing of prototypes. The extensive testing phase planned after prototyping may seem like an unnecessary delay. Yet, it stands in stark contrast to the high-risk, high-reward mentality that often permeates aerospace development. This approach emphasizes risk management and reliability, suggesting that taking the time to test thoroughly can prevent costly failures and setbacks in later stages. 7. Technological innovation as a core focus. The emphasis on technological innovation through 3D printing and rapid prototyping may seem risky compared to traditional proven methods of rocket construction. However, this focus on cutting-edge technology is indicative of a larger trend in the aerospace sector, where new technologies are not merely adjuncts but central to the development strategy, challenging the status quo that values established methodologies over innovative solutions. In conclusion, the development of the Terran rocket by Relativity Space highlights counterintuitive perspectives that challenge traditional aerospace paradigms, focusing on innovative manufacturing techniques, adaptable designs, and systematic testing to redefine expectations in the industry. The report on the implementation of Relativity Space's Terran rocket by Q4 2025 contains several critical elements that may be overlooked by the general public, particularly regarding the implications of advanced 3D printing technology and the structured development phases of the project. Significant details often overlooked. 1. Advanced 3D printing techniques. Importance: the allocation of $750 million towards advanced 3D printing techniques for the Terran rocket is a transformative aspect of the project. While many may recognize 3D printing as a method of manufacturing, the nuances of how these techniques can significantly alter aerospace production are often underappreciated. Significance: 3D printing allows for rapid prototyping, which can reduce the time and cost associated with traditional manufacturing processes. This technology can lead to the creation of complex geometries that would otherwise be impossible or prohibitively expensive to achieve using conventional methods. The ability to quickly iterate designs also means that any potential issues can be resolved faster, which is particularly critical in the aerospace sector where safety and reliability are paramount. 2. Phase development approach. Importance: the structured 4-phase development approach, design and engineering, prototyping and testing, production and integration, launch preparations, is a meticulous strategy that emphasizes careful planning and execution. Many may overlook the significance of this phased approach, focusing instead on the end product. Significance: each phase is not just a step towards completion. It represents a feedback loop where insights gained during prototyping can refine design and engineering efforts. This iterative process is crucial in aerospace projects where the stakes are high and the margin for error is minimal. The clear delineation of phases also allows for better resource allocation and risk management, which are often neglected in broader discussions about space projects. 3. Regulatory approvals. Importance: the final phase of the project includes obtaining regulatory approvals, which can often be seen as a mere formality. However, this aspect is crucial and often underestimated in discussions surrounding aerospace innovations. Significance: regulatory compliance is a significant hurdle that can delay projects. Understanding the regulatory landscape and navigating it effectively can make or break a space launch initiative. The fact that this phase is included as a critical part of the timeline highlights the importance of adhering to safety and operational standards set by governing bodies, which many may not fully appreciate until they encounter project delays due to unforeseen regulatory challenges. 4. Market implications of a successful launch. Importance: the report hints at the broader market implications of the Terran rocket's successful launch, particularly for commercial and government payloads. However, the significance of this market entry may not be fully recognized by the public. Significance: a successful launch of the Terran could position Relativity Space as a key player in the space launch market, which is becoming increasingly crowded with entities like SpaceX and Blue Origin. The ability to offer a reliable and flexible launch service could open up new opportunities for commercial partnerships, payload delivery contracts, and even international collaborations. The strategic importance of establishing a foothold in this competitive landscape is often overshadowed by the excitement surrounding the technology itself. Conclusion: the implementation of the Terran rocket by Relativity Space is not just about developing a new launch vehicle, it represents a paradigm shift in how rockets can be designed, produced, and launched. The integration of advanced 3D printing technology, a meticulous phased approach to development, the necessity for regulatory compliance, and the potential market implications are all essential components that contribute to the significance of this project. Understanding these elements is crucial for grasping the full impact of Relativity Space's innovations on the future of aerospace. The implementation of Relativity Space's Terran rocket, scheduled for Q4 2025, marks a significant development in the aerospace industry, particularly due to its innovative use of advanced 3D printing technology. Below are the 4 most valuable points for in-depth analysis and discussion. 1. Innovative 3D printing techniques. Relativity Space's reliance on advanced 3D printing techniques is a game-changer in rocket manufacturing. This approach enables the company to produce rocket components with less material and time compared to traditional methods. The implications of this innovation are profound. Cost reduction. By minimizing waste and optimizing production processes, 3D printing can significantly lower manufacturing costs, making space launches more economically viable. Rapid iteration. The flexibility of 3D printing allows for quick modifications and iterations of rocket designs, facilitating a more agile development process. This adaptability is critical in responding to changing market demands or technological advancements. Customization. The ability to produce tailored components can enhance the performance of rockets for specific missions, whether for commercial payloads or government contracts. These advantages position Relativity Space to not only compete with established players in the aerospace sector but also to redefine operational paradigms in rocket manufacturing. 2. Structured development phases. The Terran project is organized into 4 key phases, each building on the previous one and ensuring a systematic approach to development. 1. Design and engineering. This initial phase emphasizes creating reusable and efficient designs that can adapt to various payloads. The focus on engineering excellence sets the groundwork for the rocket's capabilities. 2. Prototyping and testing. Extensive testing is vital to validate designs and technologies before full-scale production begins. This phase mitigates risks associated with launch failures and ensures reliability. 3. Production and integration. The transition to full-scale production leverages the efficiencies gained from 3D printing, allowing for faster assembly and integration of components into the final rocket structure. 4. Launch preparations. Finalizing integration with ground support systems and obtaining regulatory approvals are critical to ensuring that the Terran is ready for its inaugural flight by the end of 2025. This structured approach reduces risks and enhances the likelihood of a successful launch, showcasing Relativity Space's commitment to meticulous planning and execution. 3. Significant funding allocation. The project has secured $750 million in funding, primarily directed toward enhancing 3D printing techniques. This financial backing is crucial for several reasons. Research and development. The funding will support ongoing R&D efforts to refine 3D printing technology, ensuring that the Terran utilizes the most advanced manufacturing capabilities available. Resource allocation. A substantial budget allows for hiring top talent, acquiring cutting-edge equipment, and establishing necessary facilities to support rapid development and production. Market positioning. Adequate funding positions Relativity Space to compete more aggressively in the space launch market, potentially allowing them to offer lower prices or more flexible services than competitors who rely on traditional manufacturing techniques. The infusion of capital is an essential component of the overall strategy to establish the Terran as a reliable launch option for commercial and government payloads. 4. Market impact and competitive landscape. The successful implementation of the Terran rocket could significantly alter the competitive landscape of the aerospace industry. Emergence of new players. Relativity Space's innovative approach may inspire other companies to adopt similar manufacturing technologies, leading to a broader shift in the industry towards more efficient and cost-effective production methods. Increased launch capacity. The Terran is designed to accommodate various payloads, which can increase overall launch capacity and frequency, benefiting satellite operators, research institutions, and government agencies. Potential partnerships and contracts. A successful launch could open doors for partnerships with NASA and other governmental agencies, as well as commercial contracts with private companies looking for reliable launch services. The impact of the Terran's successful implementation extends beyond Relativity Space, potentially catalyzing changes across the aerospace sector and influencing future trends in space exploration and commercial launch services. Conclusion. In summary, the implementation of Relativity Space's Terran rocket by Q4 2025 represents a pivotal moment in aerospace innovation, primarily driven by advanced 3D printing technologies and a structured development process. The significant funding allocation enhances R&D capabilities, while the potential market impact may redefine competition within the industry. As this project progresses, it will be essential to monitor its developments and the ramifications they hold for the future of space exploration and commercial launches. Here are 3 famous historical cases that share similarities with the implementation of advanced technologies: funding allocation and innovative design processes akin to the development of Relativity Space's Terran rocket. 1. Apollo Program 1961 to 1972. The Apollo program was a pivotal initiative by NASA aimed at landing humans on the Moon and returning them safely to Earth. The program consisted of several key phases: initial design and engineering Apollo 1, extensive testing Apollo 7, and the ultimate goal of lunar landing Apollo 11. Significant funding was allocated to develop advanced technologies, including the Saturn V launch vehicle and the lunar module, which required extensive research and development in various engineering fields. The Apollo program not only showcased the effectiveness of structured phases in project management but also highlighted the importance of innovation in overcoming technical challenges, much like the approach Relativity Space is taking with its Terran rocket. 2. Space Shuttle Program 1972 to 2011. NASA's Space Shuttle program represented a major leap in reusable spacecraft technology. Like the Terran, the shuttle went through several phases, including design, prototyping, and testing, followed by production and operational deployment. The program's funding was substantial, amounting to billions of dollars, aimed at developing reusable launch systems, which significantly reduced the cost of access to space. The shuttle's ability to carry various payloads and conduct missions ranging from satellite deployment to servicing the Hubble Space Telescope mirrors the flexible capabilities that Relativity Space aims to achieve with the Terran rocket. 3. Boeing 787 Dreamliner 2003-present. The development of the Boeing 787 Dreamliner involved innovative manufacturing techniques, including extensive use of composite materials and advanced production methods. Similar to the Terran rocket, the 787's development was divided into phases: design and engineering, prototyping, testing, and production. Boeing allocated significant funding to research new technologies that would enhance efficiency and reduce costs. The challenges faced during the Dreamliner's development, including supply chain management and production setbacks, bear resemblance to the potential challenges that Relativity Space may encounter while implementing their advanced 3D printing techniques for the Terran rocket. These historical cases illustrate the importance of phased development, innovative technology, and significant funding, paralleling the approach taken by Relativity Space in developing the Terran rocket. Future outlook: implementation of Relativity Space's Terran rocket by Q4 2025. Overview of predictions. As the aerospace industry evolves rapidly, the implementation of Relativity Space's Terran rocket by Q4 2025 is poised to significantly impact space transportation. With advancements in 3D printing and a structured development process involving $750 million in funding, the future of space travel looks promising. This outlook will explore 4 key phases of the Terran's development, the expected outcomes of these phases, and broader implications for the aerospace sector. Phase 1: Design and Engineering, Q1 2022, Q2 2023. Relativity Space's innovative approach to rocket design, primarily through advanced 3D printing technologies, is set to redefine aerospace engineering, as the company focuses on leveraging its proprietary techniques. We can anticipate a future where customization and flexibility, the ability to rapidly iterate designs, will allow for tailored solutions to meet specific payload requirements. This adaptability may lead to a new generation of rockets capable of serving diverse missions, from satellite launches to interplanetary exploration. Cost efficiency: By minimizing material use and streamlining production timelines, the Terran could significantly reduce launch costs. This pricing model may democratize access to space, enabling smaller companies and nations to participate in space exploration. Sustainability, enhanced recycling and resource-efficient manufacturing processes will likely emerge, contributing to a more sustainable aerospace sector. Phase 2, Prototyping and Testing Q3 2023, Q1 2024. The prototyping and testing phase will be critical in establishing the Terran's reliability and performance. Predictions for this phase include increased testing rigor. Extensive testing under simulated launch conditions will not only ensure the rocket's safety but also set new standards for future aerospace projects. The lessons learned here could lead to enhanced safety protocols industry-wide. Public and investor confidence. Successful test results will bolster investor confidence, attracting further funding and partnerships within the aerospace community. This phase could also encourage collaboration with government agencies for potential missions. Technological innovations. Challenges encountered during testing may spur innovations that ripple through the aerospace sector, influencing the development of next-generation rockets and technologies. Phase 3, Production and Integration Q2 2024, Q4 2025. As production begins, the focus will shift toward integrating various components into the final rocket structure. Key future predictions include streamlined manufacturing processes. The use of advanced 3D printing techniques will enable faster production cycles. This efficiency may become a benchmark for the industry, prompting other companies to adopt similar methodologies. Job creation and economic growth. Increased production and integration activities will likely lead to job creation in the aerospace sector. Local economies surrounding manufacturing facilities may experience significant growth as demand for skilled labor rises. Global partnerships. As the Terran emerges as a viable launch solution, international partnerships may form to facilitate collaborative missions research and technology sharing. Phase 4, Launch Preparations Q4 2025. The final phase will culminate in the inaugural flight of the Terran rocket. Here's what to expect. Successful launch and operational readiness. The successful launch of the Terran will position Relativity Space as a key player in the aerospace industry. This event may lead to increased demand for launch services, competing directly with established players like SpaceX and Blue Origin. Enhanced market competition. A successful launch could stimulate competition in the space launch market. This competition may drive down costs and improve service quality, benefiting customers and the broader commercial space sector. Inspiration for future generations. The Terran's launch will likely inspire a new generation of engineers and scientists, encouraging interest in STEM fields and fostering innovation in aerospace technologies. Broader implications for the aerospace sector. The advancements embodied in the Terran project could have far-reaching implications for the global aerospace industry. 1. Shift toward modular rocket designs. The industry's reliance on modular designs made feasible through 3D printing technologies may lead to more versatile launch vehicles capable of adapting to various missions. 2. Increased focus on reusability. The emphasis on reusability in rocket design will likely become a norm, reducing the cost of access to space and enabling more frequent launches. 3. Rise of new market players. As barriers to entry lower, emerging companies may disrupt traditional aerospace paradigms, fostering innovation and expanding the market. 4. Collaborative space exploration. The potential for public-private partnerships in space exploration could increase, leading to more ambitious projects including lunar missions, Mars exploration, and beyond. 5. Environmental considerations. With sustainability becoming a priority, the aerospace sector may adopt eco-friendly practices, focusing on reducing the carbon footprint associated with rocket launches. Conclusion. The implementation of Relativity Space's Terran rocket by Q4 2025 stands to reshape the aerospace industry through innovative design, advanced manufacturing techniques, and a commitment to sustainability. As each phase unfolds, the implications will extend beyond the immediate project, influencing market dynamics, fostering competition, and inspiring future generations to explore the cosmos. The next few years will be pivotal in determining how the aerospace landscape evolves in response to these groundbreaking developments.